Okay, this is the video solution for problem number 1 of assignment number 6, which is given to lab 51. Now, you are you're expected to submit this assignment or by a deadline, which is Wednesday, June 30th at 12 noon, 12 p.m. So this is after you return from the summer break. You're coming back on Monday from the summer break, and 2 days later, which is June 30th, you are supposed to have submitted this assignment. Okay. Now, the difference between Lab 51, assignment Lab 51, and Lab 52 is that for 51, I'm asking you to submit problem 1, and for 52, I'm asking people to submit problem number 2. Okay. This video, I will only do 51 that you're expected to submit. And if you want to see how 52 is done, how problem 2 is done, you should go and consult the video for lab 52. Okay? All right. So the problem is a buckling problem. You're asked to model the buckling of a cylinder. One end is clamped, the other end is subjected to compressive load of P, and the nominal radius is 12 inches, and the height is 48 inches, 48 by 12, and the thickness of the wall is 1 inch. Okay, and you're asked to use shell elements to do this, and these are the parabolic type, and these are the nominal. This is the nominal size of the element. Okay, so let's do it. Single part. Let's start with the part file. There we are. And because we are modeling a cylindrical shell, in other words, surface, we're going to go to generative shape design. So on this plane, I'm going to sketch a circle. You're not expected. You're not supposed in this problem. You're not supposed to use symmetry at all, because it's very dangerous in buckling. You may get loads that uh, uh, actually collapse before you predicted the load, because you took symmetry into consideration. No symmetry should be taken into consideration when you do buckling or natural frequency calculation, unless you know what you're doing. Okay, so this is diameter of 24, radius of 12. Okay, let's fit this thing. There we are. And then we're going to exit, and we're going to extrude it by 48 inches. There we are. Okay, so let's save this thing. File, save management, save as, desktop, new folder, and this is lab 51, and that is problem 1. Problem 1. For problem 2, you should see lab 52 solution. Okay, now we are told that this is made of aluminum, so let's make it out of aluminum. Metal, aluminum on this part, we close it. This is done. Now we're going to go to generative shape design. Generative shape design. In order to do buckling in CATIA, first you have to do a static analysis, one static analysis, and then buckling. So say OK. Let me change the rendering here, right there. I don't need this bottom sketch. We hide it. Okay. So we're going to measure the shell element right there. We are asked to use parabolic. We're asked to use parabolic with the size of 2, something like that. And the thickness of this shell is right there. And that thickness, you're told, is 2 inches. No, wait a minute. Let me see for a second. 1 inch. Sorry, wall thickness of 1 inch. So 1 inch. Good. So the bottom is clamped, and the top, we're going to put 1 pound on it. Okay, just 1 pound in the direction Z, or negative Z actually. Just 1 pound. So that is -1. Okay, you can see that right there. You see? Okay. So let's save this thing. File, save management. File, save management. The analysis, save as. In that folder, Lab 51 Problem 1, default name. You might say, why are we doing static analysis 1 pound? So that 1 pound is a dummy load that you're going to there, and when you do buckling later on, you're going to multiply 1 pound by that buckling factor. It's going to give you buckling load. Okay, so let's run it. Nothing fancy is going to happen. This is just going to go down. Obviously, this is going to compress because this is not the buckling problem yet. All it is a, you see, all it is a compression problem. That's all. Let's deactivate this. And now you're going to say insert buckling case. See that? Buckling case. It's going to ask you, okay, where is that solution that you ran? Where is that reference solution, static solution that you ran? Well, you ran it. You expand static case. You expand this row. You select the static case. It's going to put it in there. And you say, okay, and done. And then run it. Done. Look at the first buckling mode. It's going to go like that. Okay. And if you double click on this and you look at occurrence, see that occurrence tab? Okay. So it's, you take that, you multiply it by your 1 pound, and you get your buckling load. Okay. So to create a shape like this, you need 10 million pounds. Okay, let's look at the other ones, by the way. Now, we are not assessing the correctness of these. It's just that under this mesh, under the assumptions that you have made, if you want to, the smallest, and under assumptions of linear buckling analysis, which is not conservative at all, in real life, this will collapse under loads considerably less than this. Okay, but that says 10 million pounds. Okay, all right. Okay, so let's keep that in mind. This actually answers the question to this problem, 10 million pounds, and that is really, this is a unreasonable answer, but that's what linear buckling analysis predicts. You got to be very careful with linear buckling analysis. Okay, I don't think 10 million doesn't make sense. Okay, but anyway, that's what it is. So let's stop this, and we do the uh, I will do the second problem, but on the lab 52. Okay.